today's world, as the population grows, the demand for energy increases. To help meet this demand, gas will form an increasingly important role. There are enormous quantities of natural gas in the world, but much of it is in areas far from where the gas is needed. To move this cleaner burning fuel across oceans, natural gas must be converted into liquefied natural gas or LNG that is much easier to transport and store. So, how is LNG produced? The natural gas gets cooled to temperatures down to approximately minus 162 degrees Celsius, shrinking its volume by almost 600 times. In a typical LNG plant, treated natural gas enters a cryogenic distillation tower, known in the industry as a scrap column, producing a liquid and a gas stream. The gas stream then enters the main cryogenic heat exchanger where the liquefaction occurs. The LNG is then depressurized and sent to storage. Natural gas extracted from the ground contains impurities such as carbon dioxide, hydrogen sulfide, and water that must be removed first. Next, remaining lighter natural gas liquids, mainly propane and butane, get removed by the scrap column. However, if the column efficiency is not high enough, heavier hydrocarbons get carried over to the LNG main heat exchanger and block the narrow tubing networks, which will result in plant shutdowns and loss of revenue. My PhD project aims to address the blockages issues by generating a wide range of experimental data on the solubilities of multi-component mixtures, especially those similar to LNG mixtures at different temperatures, pressures, and compositions. We can then use those data to tune the thermodynamic models to improve their prediction on freeze-out temperatures. Here at UWA, we have designed a specialized apparatus to accurately measure the freezing and melting temperatures of different hydrocarbon mixtures. What you see here is the solid-liquid equilibrium apparatus. This is the air bath, and this is the high-pressure sapphire cell, so that we can visually observe the melting and freezing temperatures of different mixtures. The way the measurement works is, we first cool the bulk liquid down to about half a Kelvin above the expected melting point. We then use a peltier to cool the copper tip temperature until solids form. This is recorded as freezing point. To get the melting point, I increase the copper tip temperature until solid phase completely disappears.